Hello world, my name is Anelone. We are here at Estate Spas, Colorado for the Keystone Symposia Modeling Viral Infection and Immunity. I'm here with two amazing guests and they are going to introduce themselves.
So my name is Rob de Boer. I'm a modeler. I do biomathematical modeling in immunology. I'm one of the co-organizers of this meeting.
My name is Phil Hodgkin. I'm also a co-organizer of the meeting with Rob and Al Perelson. I'm an immunologist. I have an experimental lab, but we do quite a lot of modelling in that lab as well. And I should say I live in Melbourne.
That's really good.
So basically, the Keystone organization invited Alan Perelson to organize this meeting, and Alan contacted us to co-organize it with him. And we were basically honored because Keystone is a big organization organizing excellent meetings. So we really felt honored by the fact that they invited us to do a meeting on modeling. And modeling in immunology and virology is a relatively new field. And I think it's one of the good areas in biology where virologists and immunologists and modelers, they have learned to speak each other's language. So the modelers, they know immunology, they know virology, and the immunologists and the virologists, they appreciate the math. They've really learned that doing mathematical modeling can help to interpret their data, can bring things forward, can make things more quantitative. So the fact that the Keystone organization recognized this as a developing field, that you could do specialized symposia on, we were very happy with this invitation and gladly accepted.
I would say, in a way, immunology and the response to virus diseases is kind of at the forefront of this move of modelling into biology. It will be increasingly important. I think many experimental labs are grappling with very complex dynamic systems, and mathematics and modelling techniques are really the only way forward, and you really need to know how to use them to dissect your data and work out what's going on.
So what's the history of the field? What kind of challenge have you faced at the beginning to make this talk between immunologists and mathematicians and modelers?
Okay, that's interesting. That's a good question. So I started in this field 30 years ago, and at that time, we had very limited data, no time series, and just snapshots of systems. But this modeling community was already developing. So we would do models that were pretty speculative. And the typical picture would be you do a nice model and then you approach a laboratory and you say, I have this nice model and can you test it for me? And then the experimental people would politely say, yes, but we have a full agenda. And so you typically don't get a full positive response out of that. And I think it's the papers in this field, so David Ho collaborating with Alan Perelson and Shaw collaborating with Martin Nowak, that they established that what we thought was a slow and latent infection, the HIV infection, was really something very dynamic. So this combination of the early clinical data from combination therapy with these modeling approaches, it really made a big change in the HIV virology field. And then people in the field started to realize modeling can change their thinking, can help their thinking, can change the ideas about the field. And from then on, my experience is that it went the other way around. People in labs would contact me, they say, I have data, can you help me interpret it? So rather than that we modelers come with ideas to labs, can you test that for me? It's labs coming to the modelers, can you help me interpret data? And that has been a revolution. And from that, I think this whole field emerged. That's why we have this community right now of people of immunologists and virologists that appreciate mathematical modeling, but also modelers that really know their immunology and virology. It's no longer elegant, beautiful mathematical models, but they are dealing with the dirty data, and they know what they are talking about if they present a model.
So is it like magic?
No, it's something that evolved from and if you read these old papers back, it's really a surprise, because it's the approach that they did. They did just the linear regression on some clinical data. So it was utterly simple, but it's changed the field. But,
yeah, I'd say that's what we're all looking for. Some complicated process that looks like it's very difficult to work your way into, and then with a little bit of modelling, a little bit of insight, a little bit of theory, you realise that in fact you can study it and you can extract a lot of information from it, and in a way that allows you to manipulate it to some benefit in the future. So that's kind of the goal, and this example of HIV is showing that it's possible.
So as immunologists, what do you expect from modelers?
Well, my experience is a little bit different. I come from the experimental side compared to Rob, who's coming from the theoretical side. And I also come from a geographically isolated area in originally Perth, and I didn't realise I could find a modeler to help me, so I tried to learn myself. So I'm sort of a self-taught modeler, and in the end I find that quite useful in the sense that I can design the experiments in a way that I know I can use to build models, and so working on both sides I find helpful. And I think the same is true even when you have a collaboration between a modeler and someone in an experimental field. The more they know about what each other is doing, the better it's going to go, I would say.
So will you encourage that more into education at the master level or even down at the undergraduate level, that people learn more about both fields? I think it's more or less getting the mindset of both fields, not so much the technical skills to be perfect in both skills.
Yeah, that is true. So I teach courses to biology students in our university in Utrecht, and then all first year biology, all bachelor students get exposed to some level of modeling, and I think most of them don't like it, but I think it's very important that they know it exists, and very often later in the career, if the master students do projects, they remember, hey, there was this modeling approach, and then they would come back to our group and say, now I collected this data, I remember that with modeling you can become more quantitative, get more, if it's very complicated data, better think about it, become more crisp. So I think it's indeed we have to change our education to biology students that become immunologists later in their career. In general, they have to know modeling exists, and biology is changing. We are creating so large and sometimes complicated data sets nowadays. You really need some formal help to understand what's going on.
Yeah, and at the end of the day, the ultimate goal of science is to have a theory or a model that encapsulates in a very simple form a very complex field, a set of rules that you can use to predict what will happen. So in a way, ultimately, biology is being very complex and modelling hasn't played a huge role, but increasingly it has to move in this way, because that's the way science progresses.
As you said, you had an amazing day today at the Keystone Symposia with a lot of talks on HIV, latency and immune response. So what was your highlights of the day?
For me, it's a little outside of my field, HIV, so I learned a lot about reactivating the virus, about particular drugs that can do that, some ways of stimulating the immune response that reactivate HIV in a way that potentially allows the immune system now to delete the infected cells and potentially clear the latent infection. So that was a revelation to me and very exciting, I think, for that field.
Yeah, for me, so the opening talk of Bob Siliciano was really superb. There is this enormous controversy whether or not the virus is still replicating during therapy, and he very clearly laid out the different ideas about this and what the evidence is pro and con, and he introduced the topic very well to the whole audience. So I think it's a great example of how he knows that he's talking to a modeling audience, and he described these dose-response curves, so he combines some math in his talk, but he clearly gives an overview of all the immunology and virology that is involved. So that was a beautiful introduction for the whole day.
What about the evening session in which you gave a presentation?
Yeah, so several of those talks I know. What I find extremely inspiring is that we started at 8 o'clock this morning. It's 9 o'clock now in the evening. We have had poster sessions and afternoon sessions, and everybody is still active. We're all excited about the talks that we are getting, and
some of us flew in from Australia yesterday as well.
Yeah.
It was very exciting. Yes, we had a fantastic talk from, I'd say, Andrew McMichael as well, about some very unusual ways that monkeys respond to a version of the monkey version of HIV. Very unusual way of dealing with the virus and potentially important for designing vaccines. So that was also a highlight for me.
So the last section of this postcard is towards encouraging young people in this field. So I will first start by asking, what do you like about your job or your kind of research?
What I like about being a sort of theorist in immunology is that you can be pretty broad. You're asking the bigger questions. You're not describing a detailed small element of some biochemical pathway, but you have to really think about the somewhat larger questions. You have to have a broad knowledge of the literature, and you can approach this with this modeling approach. So in this area, in this interdisciplinary area of bringing immunology, virology and theory together, you can be broader, and that is something that I like very much.
That is a fantastic feature. The other feature about that is the thrill of knowing that anything you discover in this field is potentially applicable to a clinical setting, and so it can be translated. So we work at a very fundamental level to understand how viruses work, how they're infecting cells, how the immune response deals with them, and anything we can learn potentially can help us design a vaccine or a therapy that can have real benefits in the community. So it's the thrill of doing fundamental basic science at a cutting edge level and knowing that at any time you can make a significant difference to human health.
So in order to reach that level, which kind of skill of mindset young people will need to be successful?
Curiosity, imagination, and train themselves in all the skills.
Yeah, be broad. That is, don't specialize too early. Learn different techniques. Don't be afraid of a little bit of math, because the math is not so difficult.
Yeah.
The computer does it all.
The computer does it all. You only have to understand what you're doing.
Ask big questions, and if you get stuck, you can find experts like Rob.
Or Phil.
I would like to thank you very much for being part of this podcast. It has been enjoyable, and I look forward for amazing days at this conference as well.
Okay.
Cheers.
Thank you too.
Thank you.